The planet we live on is unique and fascinating. We need to be aware of the fact that only if we carefully use the valuable resources of this planet will we be able to ensure its and our survival. Nowadays, CO2 is considered the main cause of global warming, but knowing more about it can help us understand the exact magnitude of the problem and find solutions. So the question is, CO2, problem or resource?
I'm Quirino, Professor of Chemistry at the Polytechnic University of Milan, author of many publications and inventor of the porous mass. In 1927, together with my son Bernardo, I founded SIAD. I'm here today to talk about CO2. Let's start with a game. Ask 10 people these 3 questions. 1. Can we live without water? 2. Can we live without sunlight? 3. Can we live without CO2? All will surely answer that we can't live without water, and that if the sun dies, life on Earth would end and we would freeze to death. But you might get different answers about whether we can live without CO2. And many will tell you that we can live without CO2. That's wrong. CO2 is just as essential for life on Earth as water and the sun. And I'll prove it to you. CO2 is life, and I'll show you.
What we're looking at is a nice plate of hot spaghetti. Why do we eat such food? The most common answers are because we're hungry and we like them. We actually eat pasta, bread and many other foods because they give us the energy we need to keep our bodies going. And you won't believe this, but the organ that consumes most of our energy is the brain. So that piping hot pasta is our fuel. Our car's engine burns gasoline and in this way releases energy. Similarly, our body's engine converts the carbohydrates contained in bread and spaghetti into energy. As part of this oxidation process, our body releases waste gases, and guess what? These are the same gases emitted by a car engine. CO2, carbon dioxide, and H2O, water. And we hardly produce any CO2 at all. Just by breathing, we each emit 1 kilogram of CO2 a day. There are striking similarities between the fossil fuels that power cars, aircraft, industries, and entire cities, and the food that keeps all terrestrial animals going. In these 2 cases, energy-rich substances are burned. In both cases, CO2 and water are also produced as waste.
It's time to find out more about this much talked about CO2, or carbon dioxide, or even carbonic acid gas. For convenience, we will refer to its classic name, carbon dioxide, in the CO2 formula.
Carbon dioxide is an extremely simple molecule composed of 1 carbon atom and 2 oxygen atoms with a linear structure and a key feature. The bond between carbon and oxygen atoms is remarkably strong and hard to break. This requires a great deal of energy, which is why recovering carbon from CO2 to obtain something useful, such as sugars or carbohydrates, is no easy feat. CO2 is an invisible gas. It is colorless, tasteless, odorless, so we don't realize if it's around us. If only we could see CO2, we would instantly realize just how much we produce. Try turning on a gas hob, for instance. When the spark ignites the gas, a flame comes out, which combines with oxygen from the air, releasing CO2, water, and energy. We cannot see any of the gases that have reacted to the carbon dioxide that has formed, so it looks like there is none left after making coffee, but it isn't so. Think of a car with a diesel engine. Burning 1 liter of diesel produces 2.6 kilograms of carbon dioxide. If we were to travel from Milan to Bologna, we would emit more than 30 kilos of CO2 one way, like 2 full suitcases. And by the time we scrap our car, after 200,000 kilometers, it will have emitted 31.6 tons of carbon dioxide, which is 450 times our weight. What is less surprising is that at some stage, all this CO2 has built up in the atmosphere. Carbon dioxide is a gas, but if we lower the temperature to -79 Celsius, it will turn into a big block of ice. Not exactly the kind of ice we're familiar with, but a special kind of ice, known as dry ice. It's so called because liquid CO2 doesn't form.
One experiment you can carry out in the lab at school is to throw some water on dry ice cubes. You'll see a turbulent boil start all of a sudden, caused by the CO2 molecules wanting to form a whirlwind of beautiful gas bubbles that will violently erupt, rising to the surface. As we know, CO2 gets a bad rap, and it's actually considered responsible for climate change. But unlike other substances, it isn't toxic, while its close relative, carbon monoxide, also known as CO, is toxic. Then again, if it were toxic, would you be happy to drink a beer? Or a glass of Prosecco? Or carbonated mineral water? These drinks are all rich in CO2, and the tingling sensation of bubbles stimulates our palate. By the way, do you know when carbonated mineral water was invented? Well, you'd never guess it. 200 years ago, in 1783, a certain Mr. Schweppe came up with the idea of adding a newly discovered substance to water: carbon dioxide. He founded a company that sold tonic water. Schweppes isn't a recent product. It was invented before the French Revolution.
As in other cases, the saying, "too much is bad for you," also applies to carbon dioxide. If the concentration of carbon dioxide in the air rises above 10%, we have a problem as the relative oxygen concentration drops. This is what is happening in the well-known Cave of Dogs in the Phlegrean Fields, where natural CO2 emissions build up at the bottom of the cave, in which small dogs risk dying of asphyxiation. Basically, CO2 is harmless, which is why it's used in various fields. But this would not be possible if we're even slightly toxic. For instance, dry ice is added to grape bunches right after they're picked in order to cool them so as to prevent spontaneous fermentation due to the yeasts they contain. CO2 has so many essential applications, from fire extinguishers to food preservation, from the paper industry to decaffeinated coffee.
So, now that we have learned more about CO2, it's time to try and understand why today many people consider it a problem. So, guys, let's now prepare to go back in time. And it will be a really big time jump, since we are talking about 4.5 billion years ago when our planet formed. That's a really long time ago. But here is an example to help you understand. Let's suppose the Earth's history was condensed into 6 days, Monday to Saturday, and that the Earth was born at midnight on a Monday.
For 3 days, until Wednesday night, the Earth is heavily bombarded with meteorites, comets, and asteroids, which make it an inhospitable and uninhabitable planet. But such impacts result in large amounts of 2 very important substances, water and carbon. During this phase, a CO2-rich atmosphere forms. Then, the meteor collisions suddenly stop and something truly extraordinary happens. Small molecules found in vast oceans of liquid water or from comet tails combine to form larger and more complex molecules that merge into a new structure, ultimately leading to the first simple forms of life. And how this works is still a mystery. They are bacteria, tiny organisms that are invisible to the naked eye, made up of just one cell. These insignificant microbes, which are present in huge numbers, start performing a function that will profoundly change our planet's history.
As a result of a complex evolutionary process, they learn to use the light coming from the sun, an inexhaustible source of energy, to convert CO2 and water, which abounds on Earth in sugars and carbohydrates. This is photosynthesis, the fundamental process that made life possible, through which CO2 and water are converted into an energy-rich molecule, glucose, in the formula C6H12O6, which consists of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms.
With cyanobacteria, this is what the first bacteria were called, we get to around midnight on Wednesday, 2.5 billion years ago. From this very moment, beautiful life forms begin to evolve, and the Earth will never be the same again. Billions and billions and billions of cyanobacteria incessantly convert water and CO2 into carbohydrates, consuming almost all the CO2 that the atmosphere is made up of. After a billion years of incessant, intense activity, about a day and a half on our scale, the amount of CO2 left is very little, 0.03%, which is nothing.
There is so little CO2 that in order to measure it, we use a rather peculiar unit, the part per million, or ppm. 1 ppm is like 1 gram per ton, or 1 resident of Naples out of the whole city. 0.03% is equal to 300 parts per million. And since this is what we'll be talking about today, it's best to get familiar with it.
Through photosynthesis, not only are CO2 and water consumed, but massive amounts of oxygen are also produced. Living organisms learn to thrive in a world that is rich in this substance, which they use to burn the sugars and carbohydrates they feed on so as to efficiently produce the energy they need to live. Here, all living beings, from earthworms to sea lions, from algae to daffodils, are part of nature's grand cycle, in which CO2 and water, thanks to solar energy, are turned into food in order to provide energy for superior living beings. In turn, by breathing, they release carbon dioxide that recirculates in a perpetual cycle. Life forms multiply, and Earth is populated with many species of plants and animals, and so the planet is covered in great forests. So it's now Saturday morning. On Saturday afternoon, at around 4 p.m., dinosaurs appear, but they become extinct just 5 hours later, at 9 p.m., when an enormous asteroid hits the Earth. It has been almost a week now, and there is still no sign of man. Man does not appear until Saturday night, 23 seconds before midnight. This is the age generally attributed to sapiens. 200,000 years old on an actual scale. Seems a lot, right? But 23 seconds and 6 days is very little. Christ is born a quarter of a second before midnight, and the Industrial Revolution takes place only a 40th of a second before midnight. We now know that humans have existed on Earth for a very short time, a fleeting moment, only a fraction of time when compared to Earth's history. Nevertheless, in 1/40th of a second, humans managed to wreak havoc, changing things from the way they were before.
So, guys, it's appropriate to say, and man invented machines, since that is exactly what happened. In the early 1800s, during the Industrial Revolution, our great-great-grandparents began replacing donkeys, horses, oxen, and even laborers and farmers with increasingly advanced machines. But machines need power to work, and coal was a very useful source of energy. All the factories, mills, and ships began to use large amounts of coal. Remember the old steam trains seen in Western movies? Coal, oil, and natural gas are fossil fuels, derived from plants and vegetables that decomposed and transformed, and then laid on the seabed millions and millions of years ago. They were then buried under thick layers of sand and rocks and remained there. Then man discovered them and started extracting them.
If the 1800s were the century of coal, the 1900s were the century of oil. Life started changing for the better, and you should know that having plenty of energy when we need it is the key to well-being and prosperity. We now know that by burning coal, oil, or methane, which are fossil fuels, we reproduce a lot of CO2 and water vapor, which end up accumulating in the air. And so way back in the 1800s, someone began thinking about the possible consequences. One of the first people to realize that CO2 may have a warming effect was the English chemist John Tyndall. He discovered that gases such as CO2 and also water and methane contributed to what later became known as the greenhouse effect. This is because the heat reaching the Earth through solar radiation is reflected by the Earth's surface as if it were a mirror. That's quite something. Without CO2 in the atmosphere to retain this heat, the average temperature on Earth would be minus 15 degrees centigrade instead of 15 degrees centigrade. That would be like spending a lifetime in Greenland in the winter. So the effect of that small amount of CO2 in the atmosphere isn't that bad. It's actually essential. As with all things, it's best not to overdo it. But in the mid-1900s, a young American chemist, Charles Keeling, realized that things were going too far. Scientists voiced their concern, but to no avail. There was a lengthy debate on whether it would significantly affect the Earth's temperature.
The history of our planet tells us that there have always been periods of very cold and very hot weather, not only in the distant past, but also in recent times, such as the Roman warm period, or Roman climatic optimum, a period of unusually warm weather in Europe and the North Atlantic that ran from approximately 250 BC to 480, which allowed Hannibal to cross the Alps. Or, more recently, the medieval warm period from 950 to 1250, which was marked by higher temperatures in certain regions. During this time, ice-free seas enabled the Vikings to settle in Greenland, while North America faced extended periods of drought.
A few extra degrees of heat could do no harm, especially for those who lived in cold countries. So there was a certain level of skepticism, and many felt it was blown out of proportion. Many years later, conclusive evidence was found by Claire Peterson, a geologist, who had a great idea to determine how much CO2 was in the atmosphere in the distant past. We could analyze 1,000-year-old ice at the poles. As the snow falls, tiny air bubbles are trapped between the snowflakes. And as the snow slowly piles up, layers of progressively older ice form. Thousands and even hundreds of thousands of years old. Inside it are air residues, even from 1 million years ago. The problem is that very deep holes need to be drilled in order to be able to extract the age-old ice that formed when man did not yet exist. Several research programs were launched in freezing Antarctica to retrieve valuable information from deep in the ice about how much CO2 there was in the distant past. By the start of the 21st century, campaigns had ended, and the result was shocking. Over 800,000 years, the amount of CO2 in the atmosphere has remained between 180 and 300 parts per million, slightly less than when Keeling had measured it in Hawaii in the early 1960s. However, since then, in just a few decades, this figure has risen to 420 parts per million, up by 40% in a short span of time. CO2 levels were rising at a rapid rate, and fossil fuels are what produced them. We had to reverse this trend and find ways to produce energy without generating CO2.
So, guys, only 150 years ago, people were riding horse-drawn carriages. Airplanes didn't exist. Homes didn't have refrigerators, TVs, or washing machines. And stoves were used for heating. Everything has changed now. We can speak across continents in real time, travel in comfortable cars, and fly over oceans in just a few hours. This is made possible by energy, which we use in large amounts.
Italians consume 4,700 kilowatt-hours of electricity per person per year, while Americans consume more than twice as much, and people from Chad only consume 12 kilowatt-hours. That's to say, an American consumes the same amount of electricity per day as a person from Chad does in 3 years. Oddly enough, without energy, our existence would not be that much different from that of Dante's contemporaries or even Mesopotamian inhabitants. Energy is a primary source of well-being, and we can't live without it. For over 2 centuries, we have been exploiting a simple and very rich source of energy, fossil fuels. Now, however, we know that this comes at a heavy price: climate change. So we have to learn to produce energy sustainably, and the way to do this is called renewable energy. What is the only inexhaustible source of energy we have? The sun. The amount of solar energy that reaches the Earth is about 10,000 times as much as all the energy used by mankind as a whole. In order to capture a fraction of this energy, solar panels, wind turbines, and hydroelectric power plants were developed, which are all sources that do not produce any extra CO2 or more or less directly rely on energy from the sun.
But I must now give you a serious warning. The transition from fossil fuels to renewable energy will not be a walk in the park. It will be a long process, not without obstacles, especially since we are consuming more and more energy. We are very good at coming up with new ways to waste it.
Cryptocurrency-related transactions alone consume more than countries such as Argentina and the Netherlands, and the CO2 emitted as a result of the internet use is estimated at 830 million tons a year, which is the equivalent to about 2% of all global CO2 emissions. Every online search impacts on our planet. By processing 3.5 billion searches per day, Google accounts for approximately, in a year, 40% of the internet's carbon footprint. 20 emails a day per user generate the same amount of CO2 emissions as a car traveling 1,000 kilometers. More than 12 billion emails are sent in an hour, which is equivalent to more than 4,000 tons of oil. It will take several decades to complete this transition if we're lucky. Meanwhile, oil and methane will continue to be burned and CO2 produced, so the temperature of the planet will inevitably keep rising. CO2 is also a highly stable molecule that does not break down and stays in the atmosphere for a very long time. A third of the CO2 produced today will still be in the atmosphere in a century. A fifth will still be there in 1,000 years, and some even in 10,000 years. We already have too much CO2, but it's set to increase further for quite some time.
What to do then? I think that we will have to learn to recover and reuse it. That is, to do what nature already does with natural photosynthesis. Scientists have been repeatedly attempting to create systems that are able to capture sunlight and use it to convert CO2 and water into sugars and carbohydrates. It's artificial photosynthesis. We have prototypes of artificial leaves that carry out this function. Unfortunately, such processes are still inefficient. But there are other ways. Remember Volta's pile? Thanks to this discovery in the early 1800s, for the first time, water was split into hydrogen and oxygen, with the electricity produced by a battery. They called it electrolysis, from electro meaning electricity and lysis meaning dissolution. We can now exploit this process on an industrial scale. With energy from renewable sources, we can produce hydrogen, a valuable substance suited to various purposes and obtained from water. Hydrogen produced in this way is clean, sustainable, and doesn't produce CO2, so it's called green hydrogen. It's the only type of hydrogen we can trust. The availability of green hydrogen will open up interesting possibilities for reusing CO2. The next step? Combining CO2 with hydrogen and producing green fuels. In fact, my chemist colleagues have discovered new ways to directly combine hydrogen with CO2 by using suitable catalysts in order to produce new green gases and even new fuels.
Green hydrogen, obtained from renewable sources, will make it possible to produce gasoline for cars or kerosene for aeroplanes obtained from solar energy, water, and CO2. They will be used to power ships, fly aeroplanes, and run factories. CO2 will be recovered and reused and will no longer build up. This is the idea behind the circular economy, a new concept that involves producing energy and using our planet's resources in a smart way. No more disposables. We will need to learn to recycle and reuse the raw materials we consume, since the Earth's resources are not unlimited, and we won't be able to continue exploiting it as we have been doing until now.
It's now possible and feasible to recover CO2 in concentrated form where it is present, such as in thermal power plants, cement factories, and industry in general, and to store it in large reservoirs in order to reuse it in industrial production cycles. So, there are solutions to the energy and climate issue, and we're working on finding other solutions. Before I say goodbye, I'd like to say one last thing, the most important one. We have realized by now that planet Earth is our only home, so we must take good care of it. This means respecting nature, helping to increase greenery, and avoiding unnecessary consumption and waste. Those who came before you unknowingly and often recklessly took advantage of the gifts the Earth gave us. We need a change of pace to embrace lifestyles and behaviors that will enable us to leave a better planet for future generations than the one we inherited. It's a huge challenge, but I'm certain we can overcome it together.